Okay, Mustapha from Olam, currently in Kajansi. Okay, that's nice. So you are Peace, not Chris. Huh? That's great. That's great. I hope you enjoyed the previous year, the festive season. I hope now very well, sound and good. We thank God that we are now back for business. This is our last year. We need to know that. Thank you for coming back in high gear. You are the earliest bird here, and that is very good. You need to keep up with that spirit. Yeah, Mr. Joshua is in the house. He's ready to teach you chemistry. So just feel at home and at school at the same time. All right, so meanwhile, you can, in case you have your colleagues who haven't joined yet, you can inform them that the class is starting soon, and Mr. Josh is just waiting for all of this. In case it reaches 8:05, I think he just begin by 10. Can inform your colleague. Mr. Center, you're welcome. Your learners are still sleeping, I think. There's only Moses Chris here. Moses Chris was joined, but the other learners are still sleeping. Let me make you the co-host. I think they would need a call, maybe. Some are not aware that we have resumed. I don't know.
Mr. Wanyan,
Yes, please.
good morning to you.
Good morning to you, sir.
And good morning to Mr. Serubiri Joshua. Good morning to most of Peace, most of Chris. Yeah, those guys are still not serious.
Yeah.
I would want to know, who is this one? Most of given or most of blessing? Have you found out? There are two. Those guys are two, but
Hey,
Chris is the boy.
okay.
Uh,
He is
anyway,
most of people in the chat.
most of
Can
Peace.
you see? Yes, he's in the chat there.
Okay. The good thing is I'm seeing Mr. Joshua around. That is good. Hey, since Mr. Joshua is around, he will start as soon as he feels like it's time to start. Yeah, there's nothing that should stop him from starting when he deems that it is the right time, even if it is on a musto, because now like 10 people have already subscribed and I'm not seeing them here. So normally we don't wait for others who are still maybe having hangover, those who take alcohol. You might find they had parties and they are
Yeah.
still fighting with the effects of too much ethanol. Is that ethanol or ethanol? Yeah,
Uh,
so I think I'll even be living here. But if Mr. Serubiri is listening, when it
is
is the right
on.
time for
Yes,
him to start, he should start.
surely.
Mr. Joshua, are you there?
I'm here, Mr. Sentai.
Okay,
I'm just waiting for those fellows.
very good. Yeah, you wait for them accordingly, and then you start. Even one person is also what they should get the service, but they are going to come. Let's just be waiting as you continue when it's time. I wish you a nice lesson. Um, have a good lesson. I'll be coming in at 10 to continue with them with biology.
It is fine. Yeah, Akumu Betty is already here. Happy New Year, Akumu Betty. I hope you enjoyed your holiday. Mr. Joshua is just ready to start teaching you chemistry any moment, anytime now.
Okay, a very good morning, members. Let me hope we are all doing well. And I just want to welcome you into 2026. And I wish you a happy, prosperous new year. So let me hope 2025 was fun, was well on your side. And if it wasn't well as expected, we just pray that 2026 be on your side. Otherwise, we thank God that He enabled us to survive or to pass through 2025 and enter 2026. For the goals that have not been yet completed, we pray that are completed within this year. So we pray for life, we pray for blessings right from God, that He enable us also to pass through this year and even to achieve more within this year. Since we are also candidates this year, we really need God's blessings to be upon us this year, because we are very sure by November we will have started our exams. So as we are preparing ourselves, let's also put God first. So before you revise, before you open the book, before you go for a lesson, at least take a moment and pray to God, at least to guide you how to read, and even to also enable you get rid of distractions and so on. At this time around, we are still going to continue with our concepts of chemistry. Last time we had talked about, or we had introduced carbonyl compounds, and I think we had talked about the nomenclature. For the case of carbonyl compounds, I talked about the nomenclature. So we are going to continue right from there, and we see how best we can get to understand the concepts under carbonyl compounds. At least we wish by the time we end these sessions, we have some new concepts in our heads, such that by the time we are learning them right from school, we don't struggle a lot to put them in our cranial cells. So far I'm seeing three members, I think. 3 members around. I will first welcome them, Mr. Chris, peace. And I'm seeing Akumu Betty together with Mwanje Morris. A very good morning. Let me hope 2025 was okay and have a happy, prosperous 2026. Thank you for attending, Thank you for keeping time. We know this is a serious year where we need to put in a lot, because we know a lot is coming towards ourselves. So we have to be very resilient. We have to be persistent. We have to be determined. And we have to be courageous. We have to be eager for whatever is going to be taught to us. We have to be very, very eager to learn it. So just make sure you are very ready each and every time to continue attending these sessions and getting these concepts. As I told you the other time, it doesn't make a sense for you to attend all the lessons, for you to attend all the coaching sessions at school or where, and you end up gaining nothing. At least each and every day you get to be taught, each and every day you revise, make sure you learn something new. But if you come here to attend a chemistry session, you go back the way you were, you learn nothing, you may not realize it, but the truth is you'll be wasting a lot of time, because the concept you would have got right now, you'll be struggling to get it in the next 4 months, in the next 5 months. Yet you spoiled a lot of time looking at it instead of installing it into your brain cells. So please utilize this little time you have, because the time is really little. The truth is you have a lot to cover at school. You have a lot, because I'm very sure when it comes to chemistry, there is still a lot. Maybe both, but in chemistry, there are a lot of things you are supposed to cover. So please get these concepts as early as possible, because the truth is we don't need you to start fidgeting, to start struggling or what. So make sure whatever you get taught, you remember it and you get to understand it. For now, I think we are going to continue because we are totally late. Some of us have joined in late, so we may not need to waste a lot of our precious time. Otherwise, a very happy new year to you guys. So I was saying that the last time we talked about the nomenclature of carbonyl compounds. We had talked about carbonyl compounds. What are carbonyl compounds? We also talked about the nomenclature, and we saw different structures. And their names, or their IUPAC names. So in that way, we also got some presentations or some exercise, which was about steel nomenclature, which some few members presented. I'm not very sure whether you guys still remember the nomenclature or the naming, but you should be remembering that concept. Because if you don't remember, you need to revisit it and practice how best you can name those different compounds. So we said under carbonyl compounds, we have carbonyl compounds which are called ketones, and we have carbonyl compounds which are called aldehydes. We saw how aldehydes are different from ketones. We said ketones are different from aldehydes in a way that, remember, the functional group in carbonyl compounds, we said it is called a carbonyl group, that carbon with the oxygen atom attached. It is called a carbonyl group. So we said in ketones, the carbonyl group is not attached, or the carbonyl carbon is not attached to any hydrogen atom. But for the case of aldehydes, the carbonyl carbon is attached to hydrogen atom. Like when you look at, if I'm to give you this, if I'm to take you back here, when you look at the first compound here, this one here, when you look at this compound it's a ketone. Why do we say it's a ketone? A mere looking at it, you can easily realize that you are dealing with a ketone. Why? Because when you look at the carbonyl carbon in this compound, or the carbon which is carrying the oxygen, that carbonyl carbon is not attached to any hydrogen atom, but instead it's attached to methyl groups. So now, since it's attached to the methyl groups, then that one, it's called a ketone. The carbonyl carbon is attached to methyl groups, not hydrogen atoms. It can be attached to aryl group, the way you see it down here. It may not be carbonyl, they may not be alkyl groups, but they can be aryl groups. The way you see this last compound, a diphenylmethanol. This one, this side you have a benzene ring, this side you also have a benzene ring attached to a carbonyl carbon. So this one is also a ketone because the carbonyl carbon is not attached to hydrogen in any way, but it is instead attached to the aryl groups or to the benzene rings. So in that way, that is, such compounds are called ketones because the carbonyl carbon is not attached to any hydrogen atom. But in carbonyl compounds, where the carbonyl carbon is attached to a hydrogen atom, for example, when you look at the, as we're going to look at it down here, because I think for this case, they were only ketones. Now, when you come up here, we have this. When you look at this compound right here, it is called propanol. Why? We are changing the naming. So this one is an aldehyde. It is not a ketone. The reason why it is an aldehyde is because the carbonyl carbon, or the carbon which is carrying the oxygen atom, is attached to a hydrogen atom. Therefore, that compound is an aldehyde. It is not a ketone because the carbonyl carbon is attached to a hydrogen atom. So therefore, that compound becomes an aldehyde. And we said the way we name aldehydes is different from the way we name ketones. How do we name aldehydes? We said we name aldehydes by removing or by substituting the suffix ane of the mother alkane with the suffix, we name the aldehydes by replacing the suffix, by replacing the suffix that is e with the suffix al. So which means the compound or the alkane, which was, let me say, propane, because we know alkane is with 3 carbon atoms, or an alkane with 3 carbon atoms is called propane. So if the mother alkane is having 3 carbon atoms, and that is propane, but because we are dealing with an aldehyde, we said we are going to remove the suffix e and replace it with the suffix al. So therefore, from propane, it becomes propanol. From butane, it becomes butanol. From ethane, it becomes ethanol. So we just replace the suffix. But what you have to know here, we just substitute the suffix of the mother alkane, that E of the mother alkane, with Al. So whatever here, methanol, propanol, ethanol, those ones, they are aldehydes. So which means the carbonyl carbon in them is attached to a hydrogen atom. So the naming in ketones, for it we said we have to replace the suffix E, or we have to substitute the suffix E of the mother alkane with the suffix ONE. So if the mother alkane is of 3 carbon atom, that is propane. So you replace the suffix E with the ONE and it becomes propanone. That's why the first one here is having 3 carbon atoms. It means the mother alkane is propanone. Then right here, we have this other one, which is butanone. So this one is coming from the mother alkane, which is butane. So replace the suffix E with ONE and it becomes butanone. So for these other ones, that is pentane 2-on, those means the mother alkane is pentane. So this one is pentane 3-on, which means still the mother alkane is pentane. Just that the position of the functional group or the position of the carbonyl group is the one which is changing from position 2 to position 3. Otherwise, you have to know that naming right in that way. So right now, I think we had looked at physical properties. We wanted to go to isomerism. We may not spend a lot of time on physical properties, but we are going to look at it briefly. Okay. So now when it comes to physical properties, what we know that the physical properties we talk about, we basically talk about of the melting point, we talk about of the physical state, and maybe the solubility. So we need to know those which are gases, those which are liquids, those which are solids at room temp. The way we said, or the way we were looking at alkanes, and we said the first 2, those are what? So the first 4, those are gases. The next 8, those are liquids. Then from that one, let's start. So it is the same thing right here. Like when we say that we are talking about a physical state right here, the physical state, we are meaning that state, or because we know we talked about those states of matter, the liquid, the gas, and solid. So we need to know those which are in solid state, those which are in liquid state, and those which are in gaseous state. So when we talk about of carbonyl compounds, this one was not supposed to be methanol. It was supposed to be methanol. It was supposed to be methanol. This was supposed to be A, not O. So methanol is a gas, but it was supposed to be methanol. So methanol is a gas. Other aliphatic aldehydes and ketones of relatively low molecular mass or weight are colorless liquids at 20 degrees Celsius. 20 degrees Celsius is what you call the room temperature. Then those with high molecular masses, of course, when we talk about of the high molecular masses, they are those which have got rings. Of course, any aldehyde or any ketone with a ring like a benzene ring, that compound has already got a very high molecular mass. So you expect it to be solid. Things like a benzaldehyde, diphenyl methanol, all those which have got rings, so long as it's a ketone or an aldehyde and it has got a ring, those ones are all solids. Together with others which are aliphatic but with high molecular masses, they are also solids. Those with relatively low molecular masses, they are liquids at room temperature. For example, ethanol. Ethanol is a liquid. Propanol is also liquid. So those with relatively low molecular masses, propanol is a liquid. Butanol is also liquid. Those with relatively low molecular masses are liquids, but those with high molecular masses, they are solids. So it is only methanol which is a gas, or which exists as a gas at room temperature. So when we talk about a physical state, that's how best we can talk about them. It is only methanol which exists as a gas. The rest, all the ketones and the aldehydes with relatively low molecular masses, they are liquids. Those with high molecular masses, especially those with the rings, which are not aliphatic, they are solids. So when we go to another physical property, that can be the solubility. Solubility, here we have talked about solubility even in alcohols, we talked about solubility in other homologous series. Whichever homologous series we talk about, we look at solubility. How do they interact with water? How is their behavior with? How do they behave with water? Carbonyl compounds, the first thing you have to understand, they are polar. And we said all polar compounds, they are soluble in water. However, solubility varies depending on the molecular mass. When the molecular mass increases, most of the time the solubility reduces. So, but what you have to know that these carbonyl compounds are polar. The way we saw alcohols, that alcohols are polar. Therefore, because they are polar, they can form dipole moments, which dipole moments can result into formation of intermolecular hydrogen bonds. So, in fact, water molecules can easily interact with carbonyl compounds via those dipole moments created. When you look at the structure down there, when you see that carbonyl group, it is the carbon is carrying a partial positive charge, the oxygen atom is carrying a partial negative charge, because we know oxygen atoms are more electronegative than carbon atoms. Now, in that way, when you bring a water molecule closer to the carbon or to the carbonyl group, you are going to see that even in the water molecule, the oxygen atom is partial negative, the hydrogen atom is partial positive. So you can easily form the so-called intermolecular hydrogen bond between the oxygen atom of the carbonyl group and the hydrogen atom of the water molecule. The moment that bond is formed, it means that compound is going to dissolve in water. So, because the compound can easily interact with the water molecules via intermolecular hydrogen bonds. So, the intermolecular hydrogen bonds are going to be created between the carbonyl group and the water molecule. So, therefore, carbonyl compounds are soluble in water. However, we said their solubility reduces with increase in molecular mass. When the molecular mass increases, of course, their solubility will have to increase. So it will have to decrease. So that's why we have said the higher carbonyl compounds with more than 5 carbon atoms and aromatic carbonyl compounds, for them, they are insoluble in water. As I've told you, that all carbonyl compounds with the rings, those carbonyl compounds, they have higher molecular masses. Because you to have a ring, it means you have a very high molecular mass. So that's why you have said carbonyl compounds which have got more than 5 carbon atoms, and the aromatic carbonyl compounds, for them they are insoluble in water. Why? Because they have got very high molecular masses. And we know that the solubility of these compounds in water decreases with increase in molecular mass. So yes, they are soluble in water because they have that polar bond, or they form dipole moments because they have a carbon to oxygen double bond, which is a polar bond. So they can interact with water via dipole moments through forming intermolecular hydrogen bonds. So in that case, you are going to find out that the carbonyl compounds or ketones which have got 1 carbon atom, 2, 3, 4, they are soluble in water. But those which have got 5 carbon atoms and above, they are insoluble in water, however much they have the polar bond. But because their molecular mass is very high, or their molecular masses are very high, they cannot dissolve in water. So in practicals, you'll easily witness this when you start doing organic practicals. You'll see that compounds like a benzaldehyde, that is an aromatic carbonyl compound, that is an aromatic aldehyde. Compounds like diphenyl methanol and others which are aromatic, all those which have got rings, they are totally insoluble in water, and some they exist as solids. So what you need to do about them, you need to heat them. So, and after heating them, you either dissolve them in sodium hydroxide, but most of them which are liquids, most of them they are liquids, however much, but there are those which are existing in a solid state, which have got high molecular masses, as we have talked about the physical state. But what you have to know, when we are testing their solubility, most of the carbonyl compounds we have in the laboratory, they are insoluble. Some are soluble, but others are insoluble, especially those which have got carbon atom 1, 2, 3, 4. For them, they are soluble, they have no problem. But those with the 5, 6, 7, and those with the rings attached, they are somehow insoluble. So, but they are very soluble in organic compounds, as we know, because these ones are organic compounds. So when you put them in organic compounds, they are highly soluble. For example, they are soluble in benzene, they are soluble in carbon tetrachloride, and other solvents which are organic in nature. Okay. So if you talk about solubility, that's what we can talk about. Okay. Then another one is border boiling points, another physical property we can talk about. This physical property, it is also based on the forces of attraction. If you remember what I told you when we were explaining the boiling points for the case of alcohols, boiling points for the case of alkanes, or what you call alkyl halides, it is the same concept we are going to use here. When you talk about boiling points, even when you are talking about we are talking about them in organic chemistry, boiling points or melting points, they depend on the forces of attraction in the compound. So, or they depend on the strength of the bonds. The stronger the bonds, the higher the melting points or the boiling points. or the stronger the forces of attractions, the higher the boiling points. Now, when you're talking about boiling points, you have to ask yourself, okay, I'm talking about carbonyl compounds. Which forces are in carbonyl compounds? The first thing, carbonyl compounds are polar. Because they are polar, we have said they can easily form dipole moments. And when they form dipole moments, they can easily form what you call intramolecular hydrogen bonds. So which means they are going to have the forces of attractions which are called intramolecular hydrogen bonds. At the same time, these carbonyl compounds, remember, they have got they have got covalent bonds. Carbon to hydrogen bond, carbon to carbon bond, carbon to hydrogen bonds. Those carbon to hydrogen bonds, those carbon to carbon bonds, they are covalent bonds. And we all know right from our inorganic chemistry that covalent bonds are held by weak van der Waals forces of attraction. So which means in a carbonyl compound, there are two forces of attractions. There is what you call van der Waals forces of attractions, which are in the covalent bonds. That's carbon, hydrogen, carbon bonds. Then we still have other forces which we have said they are intermolecular hydrogen bonds. Those are also forces of attraction. So the forces of attraction which we are calling the intermolecular hydrogen bonds, they are created as a result of having a polar bond in a carbonyl compound, which polar bond can form dipole moments, which dipole moments can easily result into formation of intramolecular hydrogen bonds. So you are going to find out that in carbonyl compounds, there are two forces of attraction. There is what you call van der Waals forces of attractions, whose magnitude increase with increase in molecular mass. Then we have got intramolecular hydrogen bonds. So we have two forces of attractions. And these two forces of attraction, they are the one which are to determine the boiling points of these compounds. So therefore, carbonyl compounds, they have got higher boiling points than non-polar compounds. Non-polar compounds like what? Like alkanes. Because alkanes, they are non-polar, they have no polar bond. So therefore, carbonyl compound, their boiling points are higher compared to the non-polar compounds like alkanes. For example, if you are to use an alkane and a carbonyl compound which have got the same molecular weight or same molecular mass, you are going to see that however much the molecular mass is the same, but their boiling points are different. Why? Because the other aldehyde, the other ketone, for it has an additional force of attraction. So you now look at these two examples here. Here you have propanol. Then you have an alkane here. The two guys, they have the same molecular mass. And because, yes, they have the same molecular mass, it is not a guarantee that they should have the same melting point or boiling point. Their melting points and their boiling points are totally different. Why? Because when you look at an alkane, in alkane, we only have one force of attraction, which is the van der Waals forces of attraction. In propanol, there are two forces of attractions. There are van der Waals forces of attractions, which are within the covalent bonds, that's carbon-hydrogen bonds and carbon-carbon bonds. And there is also an additional force of attraction, which we have called intramolecular hydrogen bonds. So, because in that propanol there are two forces of attraction, those two forces of attractions will make that carbonyl compound or that propanol to be having a higher melting point or boiling point than the corresponding or than the alkane, whose molecular mass is the same as that of the aldehyde or the ketone. So that's why in our explanation we are saying that, okay, carbonyl compound, they have higher molecular masses, so they have higher boiling points than non-polar compounds. Why? Because the oxygen atom in propanol or in these carbonyl compounds is more electronegative than the carbon atom. Therefore, the bonding electrons are pulled more towards the oxygen atom, creating a partial negative charge on the oxygen atom and a partial positive charge on the carbon atom. Now, because of that, the compound of propanol or the carbonyl compound will have to form intermolecular hydrogen bond. And those intermolecular hydrogen bonds, they are going to be as a result of those dipole moments formed, the partial positive charges and the partial negative charges. So, and because there are additional van der Waals forces of attractions between the carbon-carbon atoms and the carbon-hydrogen atoms, this one will need or will require such a compound to be heated at higher temperatures for them to be broken. So what should be in your mind is that compounds which are polar, like alcohols, carboxylic acids, aldehydes, for them they can easily form additional forces of attractions which we call intermolecular hydrogen bonds. So because of that, for them they always have higher boiling points, which is totally different from non-polar compounds like alkanes, because for them they cannot form dipole moments since they are not polar or they don't have polar bonds. In that case, they only have van der Waals forces of attractions as the only forces of attractions in them. So for them, it is easier to break them than these other polar compounds, because the polar compounds like carboxylic acids, alcohols, carbonyl compounds, they can easily form other additional forces of attractions, which you call intermolecular hydrogen bonds. So when we talk about boiling points or melting points, that's how best we can explain it. And that's how we have been explaining it even in alcohols. And I think that's how we even explain it in carboxylic acids. You just have to know that this compound is polar. Therefore, the oxygen atom is more electronegative than the carbon atom. So you are going to form partial charges. Oxygen will take a partial negative, carbon will take a partial positive. The moment you form those dipole moments, that compound can easily interact with other propanol molecules, forming intermolecular hydrogen bonds, which will have to require a lot of heat to be broken. So, which is not the case for non-polar compounds. So you have to know that. So unless someone has not got the concept clearly here, but I think we can go to isomerism. So those are some of the physical properties which we can talk about when we are in carbonyl compounds. So you already know that carbonyl compound, they can exist as gases, liquids, or solids. But the only one which exists as a gas is methanol. Liquids, those are carbonyl compounds of relatively low molecular mass. Solids, those are carbonyl compounds of higher molecular masses or with higher molecular masses. When it comes to solubility, we also explained that solubility varies with molecular mass still. However much the compounds are polar, they are soluble in water, but their solubility decreases with the increase in molecular mass. So those with the rings, they are highly insoluble, however much they are polar. Okay, so we said that we cannot talk about any homologous series and we don't talk about isomerism in that homologous series. So how are these? Please, if I told you, if you have where to note something there, because we are going to repeat this same topic, of course, when you come back, but at least you should be having an advantage when we are studying it again. Isomerism in these carbonyl compounds, if you remember very well, I think it was alcohols. Anyway, we talked about one of alcohols. But for the case of isomerism, I think I gave you this example right here last time for you to try it out. So some members tried out this example. However much you gave out a few isomers, but I remember to give you those isomers down. After calculating the empirical formula and after getting the molecular formula, I think you got this as your molecular formula. So some of us could only write these isomers down here. This, after understanding that you are dealing with a carbonyl compound, it should come to your mind that carbonyl compounds, which isomers do they form? Carbonyl compounds, the first thing, they can be ketones. The second thing, you can form aldehydes in them. The third thing, we said they are isomeric to cycloalcohols. Another thing, we said they are isomeric to diene. Is it? We said they were dienes. We said they are isomeric to that we call them, is it? Yeah, yeah. So they are isomeric to such compounds which have got a double bond and still they have got a hydroxyl group or a hydroxyl group. So they are isomeric to enols, they are isomeric to cycloalcohols, and they are isomeric to, I think, they are isomeric to what? The enols and ethers, yeah. So ethers, but in form of, in fact, we call them ethers, like ethers which have got a double bond. So this should be in your mind that I'm going to create how many isomers? The first isomers to think about when you are dealing with carbonyl compounds, that is ketones and aldehydes. Those are the first isomers to think about. Now, which other isomers are you going to think about after writing down your ketone and after writing down your aldehyde? After doing so, you are going to think about other isomers. Like what? You are going to think about enols, because we know carbonyl compounds are functionally isomeric to enols. There is a question, I think it was right from a given Moko body. Yeah, it wanted the students to use this enol or this isomer. So this isomer has different properties because it has got different functional groups, because these functional groups which are within the enols, they are different from those which are within the carbonyl compound. So now you had to think, because basing on the tests they had given down there, because it was an analytical number, basing on the tests which they had given down, they were all indicating that the compound is having a double bond, and at the same time that compound is having a hydroxyl group or a hydroxyl group. So it was not supposed, and most of the students were only writing an isomer of a ketone and that of the aldehyde, and we are stopping there, because for them, in their mind, they know that carbonyl compounds, the only isomers you can create, it's either ketone or an aldehyde. But we know very well that carbonyl compounds are functionally isomeric to cycloalcohols. They are functionally isomeric to enols, and they are also functionally isomeric to ethers with double bonds. So you have to think about that, because in such analytical numbers, you can be given tests of a hydroxyl group, you can be given a test of such a group for this double bond. And because for you, you have created two isomers, the carbon dioxide and the ketone. Of course, the tests which they are going to give you, they cannot match with the isomers you have created. So in so doing, you may not be able to write or to respond to the tasks which you have been given. So, but what you have to know that carbonyl compounds are totally functionally isomeric to cycloalcohols. The way you can see write this one here, the cyclobutanol, and they're also functionally isomeric to enols. We say the enols, those are compounds which have got a double bond, and at the same time they have got a hydroxy group. So that's how best we were supposed to answer such an item about isomers. I'm very sure all of us will know how to write isomers down. That shouldn't be our challenge. The nomenclature, we have talked about it right from up. So that means each isomer you create, you should be able to name it or to give it a name. So for the case of isomer, I think we will look at that question there. We will look at that question. I have to find it, I think, in the last minutes, and then we try it out. So, after looking at the isomerism, which isomers can we create in such carbonyl compounds? I said it should be in your mind that carbonyl compounds, if you are creating isomers, the first two isomers to think about, that is a ketone and an aldehyde. The second one is a cycloalcohol. The third one is an enol. So at least you should have around 4 isomers once you have been given a carbonyl compound. Okay, so after understanding the isomerism in these carbonyl compounds, we need to know how best can we prepare carbonyl compounds. By the way, we talked about some methods in alcohols. Even we talked about some methods in alkenes. Were there alkenes? In alkenes. So I just want you guys to give me those methods you remember. How best can we prepare carbonyl compounds? From where or from which? You tell me that we can prepare carbonyl compounds from, let me say, alcohols. You tell me how. So when you say that you can prepare carbonyl compounds from alcohols, you tell me how we can prepare it, using which reagents, using which conditions. So, but I'm very sure you remember at least some methods, because there are some methods we talked about. So remember those reactions, different reactions, which were yielding carbonyl compounds. There is a reaction in alkenes, I'm very sure, which was yielding a carbonyl compound, and I talked about it. There is a reaction, I think, even in alkenes. Let me see. Okay, it is in alkynes. There is a reaction in alkynes which can enable us to get you are going to tell me those reactions which can enable us to get the carbonyl compounds. There is a reaction in carbonyl compounds. In alkyl halides. Still, it can give us a carbonyl compound. And there is a reaction in alcohols. In fact, as all the homologous series we talked about, they can give us carbonyl compounds. So I just want someone to tell me how best we can prepare it, from where, using what, because that's chemistry, or that's when you get to know that you know chemistry. You can prepare carbonyl compounds from these compounds using this and this. Yes. I'm just waiting for you guys. Please don't forget those reactions. I told you organic seems to be easy when we are discussing it. But the problem which you guys do, you just go back and sit and you forget all those reactions. And yet you need them in synthesis and other preparation methods of different compounds. So who can remember those different methods which were yielding carbonyl compounds? Yes, I'm waiting. Because I've told you there is a reaction in alkanes. You have to be remembering it. That reaction which was yielding carbonyl compounds. There is a reaction in alkynes which was yielding carbonyl compound. There is a reaction in alkyl halides which was also yielding carbonyl compounds. And still there is a reaction in alcohols which was yielding carbonyl compounds. I just want to see whether you guys you remember these things, because those reactions are there. Because we don't pick preparation methods just, in fact, as I was writing these things down, I told you some of these reactions, we are going to look at them as preparation methods of other homologous compounds. So anyone who remembers anything about those reactions? Yes, Petronella.
Yes, I think, okay, the one of alcohol at 140 degrees Celsius can give
Petronella, at 140 degrees, an alcohol exposed at 140 degrees Celsius. Which reagents are there? Be very clear that you can prepare this from this using this and this at this and this.
Okay, the memory is not coming back very well, but it was an alcohol at 140 degrees to give you like methanol.
Are you sure?
No, not that.
Because if you talk about an alcohol at 140, then I get to remember formation of ethers, isn't it?
Ethers?
Yes. At 140, and it is an alcohol, it means you are going to get an ether. If at all you use sulfuric acid.
Okay.
Yes, who remembers any reaction right from those homologous series, how we can prepare carbonyl compound? Thank you, Petronella. Thank you for trying.
Okay.
Yes. Can I have anyone who can give us, because you can't tell me you guys that you don't remember these reactions.
You're free to raise up your hand and we choose you, or type in the chat. Or just unmute. You are free to unmute as well and tell us your answer.
So even that of alkynes members don't remember it. It seems you guys, you are not revising these things.
Teacher.
Yes,
Excuse me.
Navzan.
Yeah, I'm trying to remember, but in alkynes, we talked of an alkyne reacting with water in the presence of dilute sulfuric acid and mercury sulfate catalyst at 60 degrees Celsius.
Okay, yes. Yeah, that one could yield a carbonyl compound. Yes, that is hydrolysis of alkynes.
Yes, I remember it was
Yes.
in alkynes.
Yes, that's what the reaction I was talking about. So alkynes can be used.
Members should clap at least because they are quiet, and this one is giving a very nice answer. Should clap, yes.
So Nobzal, I was saying, by the way, the best thing, as I told you, is that you have to connect these homologous series if you have to understand the chemistry. If you cannot connect the chemistry in alkynes to chemistry in carbonyl compounds, the chemistry in alcohols to chemistry in alkenes, then organic is going to be hard for you. Because I told you this chemistry move together. And basically, homologous series like alcohols, carbonyl compounds, and the haloalkanes, they are like sisters. So their chemistry is within themselves. They share the chemistry. You will find out that reactions in carbonyl compounds that are preparation methods in of alcohols. You find out that the preparation methods of alcohols, they are the reactions of carbonyl compounds. They are the reactions of haloalkanes. So for the case of Nabuzari, that one is very fine. So I was talking about that reaction. You remember it very, guys. We even did its mechanism. So that's why I told you don't need to forget these things so easily. You don't need, because you have a lot to cover. So you shouldn't forget such stuff. Carbonyl compounds can be prepared from hydrolysis of alkynes. And during the hydrolysis of alkynes, we said we use water, we use consulfuric acid, and we use mercury sulfate at 60 degrees Celsius. And what do we get there? We get carbonyl compounds. And most of them, they are ketones. The only carbonyl compound we can get, which is an aldehyde, is methanol. If at all you call out, it is ethanol. If at all you call out hydrolysis of ethane. But the rest are going to be ketones. So that means hydrolysis of alkynes can easily give us carbonyl compounds. So that's very okay. Which other method can we use to prepare carbonyl compounds? I told you these preparation methods, they should be on your fingertips. Whichever homologous cell you go to, if they are alcohols, you say, how can I prepare alcohols? You should be knowing them on fingertips that I can use this method, from here, because they are the one which are going to help you in synthesis. Because you'll be able to know that I can convert this alkyne to a carbonyl compound. I can convert a carbonyl compound to an alcohol. So those are like a preparation methods which we are going to be using. So which other method can we use? I'm seeing some messages right here. I don't know whether they're about that.
No, that is Petronella saying that some brains have rusted. I think maybe the holiday was long for them.
Hey, do you also experience rusting of brains? or brain cells. Petronella, you are lying.
Maybe their brains are made up of, the cranium is made up of iron metal.
Petronella, you are lying. You are lying. Just anyway. Anyway, yeah, the method we have a method in alkanes. We have a method in alkanes. We have a method in alcohols. All those methods can be used. So we have only talked about the one on alkynes. Can someone give me the one of alkanes or the one of alkanes or the one of alkynes? Sorry, or the one of alcohols? Remember, I've totally lost these concepts.
They are waiting to be taken to the waiting room, and we remain with the Petronella, Nabuzare, and some other people are contributing.
Teacher,
Yes, Betty.
so I'm trying. So also ketone can be formed using acidified potassium permanganate.
On what? Yes, you're using acidified potassium permanganate, no? Betty, are you there? Seems she has gone off. Okay. But please don't forget these concepts. So the first method you can think of, it is the recent method we talked about. We can, in fact, it was under the reactions of alcohols. We said alcohols can be oxidized to carbonyl compounds. You guys remember that reaction? And I was even very clear that if we use a strong oxidizing agent and we are oxidizing a primary alcohol, we are likely to get a carboxylic acid instead of a carbonyl compound. In fact, I even listed these things down. I said, if you are dealing with alcohols, alcohols can be oxidized. Because we have three classes of alcohols, we have primary, we have secondary, we have tertiary. Tertiary alcohols, they can't be oxidized. That one we removed it. Secondary alcohols can be oxidized to ketones. And primary alcohols can be oxidized by weak oxidizing agents to aldehydes and by strong oxidizing agents to carboxylic acids. I summarized that information on the board. I summarized it very well on the board. So, if we want to get a carbonyl compound, it means we can use an alcohol. When you use a primary alcohol and you use a weak oxidizing agent, you can easily get your aldehyde. When you use a secondary alcohol and you use any oxidizing agent, whether weak or strong, you can get a ketone as a carbonyl compound. We talked about that. And we said the weak oxidizing agents we have magnesium oxide in the presence of an acid. We have chromyl chloride in presence of an acid. And we said when it comes to the strong ones, we can use what? Potassium permanganate, and you can still use potassium dichromate acidified. However much potassium dichromate can behave as weak sometimes, but when it comes to theory, right, these theoretical concepts here, we are going to use it as a strong oxidizing agent, and it will oxidize your primary carboxylic. That potassium permanganate, which is acidified, can still oxidize your primary alcohol to carboxylic. But because we want carbonyl compounds, we are going to use weak oxidizing agents like acidified magnesium oxide, acidified chromyl chloride, those weak oxidizing agents. Because for them, they oxidize primary alcohols to carbonyl compounds or to aldehydes. They can still oxidize secondary alcohols to ketones. So we can prepare. So I expect someone to tell me that carbonyl compounds can be prepared from alcohols using strong oxidizing agents, so using weak oxidizing agents. For example, a primary alcohol can yield an aldehyde using a weak oxidizing agent like magnesium oxide in presence of an acid. A secondary alcohol can yield a ketone using a strong or a weak oxidizing agent like a acidified potassium permanganate or acidified magnesium oxide. So these things, they should be in your brain cells. Don't forget these reactions. Don't forget these preparation methods. So alcohols can be used to prepare carbonyl compounds. That's via oxidation. You have to oxidize them. And by the way, I saw some members what was the paper. It's as if you guys, you were reducing now. Someone was reducing an alcohol to get a carbonyl compound. Okay, it is fine betting. So anyway, so the first method, it was from oxidation of alcohols. We can get aldehydes from primary alcohols because we know aldehydes are obtained from primary alcohols. Secondary alcohols, they give us ketones. Primary, they give us aldehydes. Secondary, they give us ketones. So, but for us to get aldehydes from primary alcohols, we use weak oxidizing agents. I told you potassium dichromate, in most of the cases, we consider it to be weak. Even in practical, you will see it. Sometimes it can give us a carboxylic, but chances are high that it can give us what? An aldehyde. So most of the times you consider it to be a weak oxidizing agent. That's why even here it's used as weak. It is only potassium permanganate, which is highly strong, that if you use it, you directly get a carboxylic acid from a primary alcohol. So we are saying that aldehydes can be prepared by controlled oxidation of primary alcohols using an acidified potassium dichromate, or I think this potassium permanganate was not supposed to be there if it is aldehydes, because the potassium permanganate is very, very strong. I think this was a chemical error. For the case of potassium permanganate acidified, it will be directly carboxylic acid. So basically, we are going to use the weak oxidizing agent here to yield the aldehyde. So since we are dealing with aldehyde formation from primary alcohols, basically remove this acidified potassium permanganate, because this one is highly strong. Instead of getting an aldehyde, you get a carboxylic acid. But we can use other weak oxidizing agents. As I've said, we can use chromyl chloride. We can use the magnesium oxide in presence of an acid, or potassium dichromate 6. So when we use oxidizing agents, we can easily yield carbonyl compound. The way you see it here, this was ethanol. Now you are having ethanol after using your potassium dichromate, which is acidified, or after using your manganese 4 oxide, which is acidified, or after using your chromyl chloride, which is acidified. You have ethanol as an aldehyde. So even this one is here. This one, that is phenylomethanol. Phenylomethanol is a primary alcohol. It can be converted to benzaldehyde, which is an aldehyde, using either potassium dichromate acidified, manganese 4 oxide acidified, or chromyl chloride acidified. So this is called oxidation. These are oxidizing agents. So when you use them, you have to heat. So now, this oxidation reaction results into formation of carbonyl compounds. So they are basically aldehydes from primary alcohols, and they are ketones from secondary alcohols. For the case of tertiary, those ones can't be oxidized. Now here we are noting, or here immediate note, that primary alcohols may undergo secondary oxidation to carboxylic acid. The aldehyde must be distilled from the reaction mixture as it is formed. Also, in order to avoid secondary oxidation, it is preferable to use dichromate 6 solution rather than manganate 7 solution, since dichromate ions are milder in oxidizing action. So this is what I told you up here, that we may not use potassium dichromate because it is very strong. It can cause secondary oxidation and you form a carboxylic acid. So if we are interested in getting an aldehyde from a primary alcohol, always use weak oxidizing agents. Weak oxidizing agents, we have said you can use acidified potassium dichromate, you can use chromyl chloride, you can use chromium ferroxide, or you can use manganese 4 oxide. So chromium 6 oxide or manganese 4 oxide. So whatever I want, you can use acidified chromium 6 oxide. You can use manganese 4 oxide acidified. You can use chromyl chloride, or you can use potassium dichromate. Those ones are weak oxidizing agents or are mild oxidizing agents. So for them, they only oxidize primary alcohols to aldehydes. They don't form carboxylic acids. But when you use potassium permanganate acidified, you are going to get a carboxylic acid, which is ethanoic here instead of ethanol. Now, sorry, what do you mean? You have new chemists and they're creative. Anyway, milder. We are talking about, like, when you say milder, it's like it's mild. It doesn't its actions in oxidizing are not so strong. Or if it's mild, it's like something which is just medium or moderate in oxidation now right here. So it's just a mild oxidizing agent. It is not a strong, or you can just use weak. So it is not a strong oxidizing agent, but instead just mild. So that's why we are saying, because it is just a mild oxidizing agent, it cannot form a carboxylic acid. So it's just a weak oxidizing agent in that way. Just to get it in a way of being weak. Milder, so if it is oxidized, it oxidizes. Its oxidizing actions are not strong as those of potassium permanganate. So now, They are summarized right here. These are some of the weak oxidizing agents: chromium 6 oxide, manganese oxide acidified in presence of heat, potassium dichromate solution acidified. All of those ones, they are weak or mild oxidizing agents. So when you are dealing with a primary alcohol and you are interested in an aldehyde, you are going to use a weak oxidizing agent. But if you are interested in a carboxylic acid, you'll have to use a stronger oxidizing agent, which is potassium permanganate acidified. But if you are interested in an aldehyde, then you are going to use a weak oxidizing agent. Okay. So that is the first reaction we can talk about if at all we want to generate carbonyl compounds. We said for the case of secondary, they are going to give you ketones instead of aldehydes. So when you oxidize a secondary alcohol, you are going to get a ketone. So that's why here we are saying the ketones can be formed by oxidation of secondary alcohols. Are you interested in getting ketones? Use secondary alcohols or oxidize secondary alcohols. Someone asked which reagents do we use? We can use the same reagents. By the way, for the case of secondary, you can use a strong oxidizing or you can use a weak oxidizing agent. So what you are going to get is a ketone. Why? Because ketones cannot be further oxidized to carboxylic acids. So even if you use a strong one, it cannot be converted, that ketone formed can't be converted to a carboxylic acid. So that's why for the case of secondary alcohols, you can use either acidified potassium dichromate, acidified potassium permanganate, whatever you want, it can form a ketone. So for the case of secondary alcohols, we use strong and weak because we know that ketones which are going to be formed, they cannot undergo further oxidation because ketones, they are resistant to oxidation, so they cannot form carboxylic acids, but instead they remain as ketones if you have used a strong oxidizing agent or a weak oxidizing agent. Okay, so a summarized example is here. If I'm to use the propan-2-ol, propan-2-ol is a secondary alcohol, as you can see it there. So because it is a secondary alcohol, you can use whatever reagent you need so long as it is an oxidizing agent. And what you are going to get is a ketone. You cannot get a carboxylic acid from it. For example, if we use potassium dichromate acidified, we are getting a ketone, which is propanone. If we use potassium permanganate acidified, we are getting still propanone. If we use the chromium 6 oxide, we are getting propanone. If we use magnesium oxide, we are acidified, we are still getting propanone. So these three, chromium 6 oxide, magnesium oxide, potassium dichromate acidified, they are weak. Potassium permanganate acidified, for it is strong, but they are all giving us a ketone. So for ketones, they cannot form carboxylic acids. So you can use any oxidizing agent you want. Some members, if you have not used those ones, sometimes you can use copper at high temperatures. You can use copper catalyst at high temperatures if you don't want to confuse yourself with the other reagents. You can just say copper at 300 degrees. Copper is behaving as a catalyst. So oxidation can be still achieved by dehydrogenation of alcohols using a copper catalyst. So if you are to use that one, it is also fine. Others can use the oxygen in presence of silver catalyst, heated silver catalyst. So still even temperatures there should be very high. So all those ones, they are reagents which can convert alcohols to carbonyl compounds. So you don't need to lack a reagent. You can use a copper catalyst at high temperatures to convert an alcohol into a carbonyl compound. You can use oxygen in the presence of the silver catalyst at high temperatures still to get a carbonyl compound you are interested in. So all those reagents can be used to convert alcohols into carbonyl compounds. So now what you have to know, if you remember aromatic chemistry or aromatic compounds, we said methylbenzene can be oxidized to a carbonyl compound or to a carboxylic acid. So methylbenzene, when you expose it to chromyl chloride, when you expose it to magnesium 4 oxide, when you expose it to chromium 6 oxide, that methylbenzene can give you benzaldehyde. Because those ones you have used their weak oxidizing agents. But if you oxidize it using a strong oxidizing agent, like potassium permanganate, you may end up having a carboxylic acid. But if you oxidize this methylbenzene using a weak oxidizing agent, you are likely to get an aldehyde. So that one, for the case of aromatic, you should also be remembering it. Okay. Okay. So right from there, we have another method you can use. Prepare carbonyl compounds. So if you remember, we talked about of geminal halides, where by the way, these reactions you have them in the book, just that you guys don't want to revise. Geminal halides, we talked about them. And we said, if you have a geminal dihalide, when you use sodium hydroxide or aqueous sodium hydroxide, you can easily convert it to a ketone or to an aldehyde, depending where the halogen atoms are attached. If they are attached at the last carbon atom, you are going to get an aldehyde. If they are attached to the carbon atom which is in the middle, you are going to get a ketone. So you have that reaction in your books. So geminal dihalides can be converted to carbonyl compounds using aqueous sodium hydroxide. So depending on the position of the halogen atoms, you can either form a ketone or you can form an aldehyde. If the halogen atoms are attached on the carbon atom, which is terminal, you are going to get an aldehyde. But if they are attached on the interminal carbon atom, you are going to get a ketone. So that reaction, we talked about it in alkyl halides. You have it in your books. So that one can still enable us to prepare what you call aliphatic carbonyl compounds. So here we are saying this preparative method is not commonly used for aliphatic compounds because of difficulty in obtaining the dichloro compounds. However, benzaldehyde can be formed using the method because the dichloro compound is always obtained. So we can still use it for the case of a geminodihalide, which is aromatic, the way you see it there. So it can still be used. Then from Grignandi's reagent, this is the one which I was still telling you about alkyl halides. If you remember where we used the Grignandi's reagent, we said we can use a nitrile with the Grignandi's reagent and we get this guy. I don't know whether you guys remember that. And we did a mechanism for that reaction. If you go back to those alkyl halides, where we talked about Grignandi's reagent, because remember Grignandi's reagent is formed from alkyl halides. You get an alkyl halide, you react it with magnesium in presence of dry ether, you get a Grignandi's reagent. We said when you react a nitrile with Grignandi's reagent and you hydrolyze that nitrile, that formed intermediate, you can get a ketone. So hydrolysis of nitriles or hydrolysis of such formed intermediates from nitriles and Grignandi's reagents can easily yield ketones or can easily yield carbonyl compounds. So this reaction, we even used it, I think, it was a synthesis, but we have been using this reaction, or we used it when we are looking at carbonyl aldehydes. Sorry, at alkyl halide. So you should be remembering it, the one of nitrile reacting it with the Grignandi's reagent to get a ketone. So please visit those notes of yours. So this 1 and 2, we are meaning there are two reactions here. When you get Grignandi's reagent, the first reaction you are going to do is to react it with a nitrile in presence of dry ether. That's the first reaction. When you do so, the intermediate formed, you are going to hydrolyze it using acidified water. So those are the two reactions. Just there we have combined them, but they are supposed to be two. So you have to know that you can prepare carbonyl compounds from Grignandi's reagent. How? You react the Grignandi's reagent with a nitrile and then you hydrolyze the intermediate using acidified water. Okay. Then another method. So another method is from acid chlorides. Now, what is an acid chloride? I know some of you have never looked at these compounds, the so-called acid chlorides. But acid chlorides, for them, the way you see, for example, carboxylic acid, CH3COOH, we replace that OH with a chloro group, and you call it acid chloride or acyl chlorides. So the way you see this one here, it's called an acyl chloride, or it is called an acid chloride because they are right from carboxylic acids. So we can use acid chlorides to get carbonyl compounds. Do you remember Lindy's catalyst? It is the same catalyst we use here. So we call this one the Rosen-Mandy reaction. So here we use still Lindy's catalyst to convert this acid chloride to a carbonyl compound. So that one I'm very sure you have not been in the know of it. So, but these reagents, you see hydrogen, poison, palladium, barium sulfate catalyst, that is the Lindy's catalyst. Or that's the composition of the Lindy's catalyst. Because I remember to give you that Lindy's catalyst. Sometimes we put there quinoline, but when we say poisoned, it means we have already used the quinoline. But if you just say hydrogen gas, palladium, barium sulfate, you put quinoline there. But if you say poisoned palladium, it means you have already used quinoline. But the best way is to just write Lindy's catalyst. Yeah, and everything gets sorted. So that Lindy's catalyst can convert that acid chloride or that acyl chloride into what you call a carbonyl compound. So should you happen to have an acid chloride and you want to get a carbonyl compound, just use Lindy's catalyst. You'll get the carbonyl compound direct. So therefore, carbonyl compounds can still be prepared from acyl chlorides or from acid chlorides. So that is another way to get carbonyl compounds. Another common method we use is the decarboxylation of calcium salts. Now this one, it has been a common method in formation of carbonyl compounds. Sometimes we heat them, sometimes we react them. But I think the common one is heating. We just heat the calcium salt, expose it to heat, and you get the compound. For example, look at this one here. This is a calcium salt. Sorry. It is calcium ethanoate, this one. Now, when you heat that salt, remember it is calcium ethanoate. Calcium has a valence of 2, which means you have 4 carbon atoms. We have 4 oxygen atoms. We have 6 hydrogen atoms in this compound here. So calcium ethanoate, once heated, it can easily give you this compound here, which is a ketone and the calcium carbonate. So basically, if you want to get a ketone, in most cases, just heat a calcium salt, like either calcium ethanoate, it can be calcium propanoate, depending on the ketone you want. So if you want a ketone of 3 carbon atoms, it means you are going to use calcium ethanoate. If you want a ketone of 4 carbon atoms, should we say 4 carbon atoms? That means you are going to use, it will be calcium. If it is 4, if it comes to heating, because remember you have to form calcium carbonate, then it means if you use calcium propanoate, there are 6 carbon atoms. So that means you're going to get a ketone of 5 carbon atoms. So when you heat calcium propanoate, you get a ketone of 5 carbon atoms. When you heat calcium ethanoate, you're going to get a ketone of 3 carbon atoms. But what you have to know, if you want to liberate or to generate a ketone or a carbonyl compound from a calcium salt, right from carboxylic acids, like a calcium ethanoate, what, you have to just heat the salt. Sometimes you can react these 2 salts together, but that one I think is kind of complicated than heating. So just have to heat the salt and you liberate your ketone. Okay. So the methods are still many, but we just have to revise them. We have the one of alkanes. We have the one of aromatic compounds by carrying out acylation. This one I'm very sure you remember it. Yeah, by the way, if you don't use calcium salt, if you don't hit a calcium salt, you can hit nickel salt, or you can hit barium salt, or you can hit magnesium salt or copper salt. So long as that salt, the element attached has valence 2. For example, you can hit a calcium salt, you can hit a barium salt, you can hit magnesium salt, you can hit a nickel salt. For example, nickel ethanoate, magnesium ethanoate, barium ethanoate, all of those ethanoates can easily give you what? Ketones. So you just need to be very keen there. But basically, here you can get nickel carbonate instead of nickel oxide. But just that nickel carbonate can decompose easily. That's why you have nickel oxide and carbon dioxide. So right here, we said instead of calcium carbonate, calcium ethanoate, we can use these other ethanoates to get ketones. So you just have to hit them and you liberate the ketones right from there. Okay, then we have this other method, which is the Friedel-Crafts acylation. This one is also very common. Those who remember aromatic compounds, we carried out acylation of benzene. In acylation of benzene, we said we use an acid chloride or acyl chloride. And that acid chloride, we use it with Friedel-Crafts catalyst to get our ketone, to get our aldehyde, and so on. So this one, we even know the mechanism. So we basically here liberate ketones. So this method of Friedel-Crafts acylation liberates only ketones, not aldehydes. So that's why when you use that acid chloride or acid bromide, you are going to get that ketone, or those ketones being formed. They are called aromatic ketones. Then another method is ozonolysis of alkenes. This one, all of us will remember it. In alkenes, we carried out ozonolysis. And we said when we are carrying out ozonolysis, we use ozone, we use carbon tetrachloride at temperatures which are below 20 degrees. After getting the intermediate, we hydrolyze it using water, zinc, and ethanoic acid. So you remember that method, because we did around 2 examples of it. So here you get 2 carbonyl compounds, depending where the double bond is. When you look at this one, the double bond is the terminal. Therefore, you are going to get 2 different carbonyl compounds. You are going to get ethanol. You are also going to get methanol. When you look at the second, the double bond is in terminal. You are going to get 2 similar carbonyl compounds. That is ethanol. Because this side, once it breaks right from here, this group will give us ethanol. This side you also get ethanol. So we said you can only get ketone from ozonolysis if at all the chain is branched. If your chain is branched, you can get a ketone. The way you see this example, here you have a methyl group Therefore, this group here, CH3C, CH3 up, is going to give us a ketone, which is propanol. The remaining part will give us an aldehyde. So, we can prepare carbonyl compounds from ozonolysis of alkenes, from Friedel-Crafts acylation of benzene, from geminodihalides, from alcohols, from hydrolysis of alkynes, from even alkanes, from heating of salts, of carboxylic salts like calcium ethanoate. All those methods can be used to prepare what you call carbonyl compounds. So hydrolysis of alkenes, that one you remember it. We said we used the mercury sulfate, water, conch sulfuric acid at 60 degrees Celsius. So here the word dilute means water and sulfuric. So even if you don't put the word conch and water, the moment you say dilute sulfuric, it means there is water. So hydrolysis of alkenes will also give us carbonyl compounds, the way you see it there. The mechanism, you already know it. So please remember, we have talked about all these preparation methods. If you want to be good at organic, if you want to pass your organic, synthesis numbers and so on, make sure that all these preparation methods we have looked at, you can easily write them down. So what is your task? Go back and summarize these methods. Make sure that you can write these methods and you can easily present them. First, make sure you can easily write the conditions, the reagents, and the correct products. So, they are not so hard, but if you get to put them into your cranial cells, then the chemistry will become very easy. We have looked at around almost 7 methods. When we look at the first method, it was from alcohols, primary and secondary. Another method, which was geminoaldehydes. Another one, I think, was Grignandi's reagent. We had the one of heating of the carboxylic salts. We had the one of hydrolysis of alkenes. We have just seen the one of Friedel-Crafts acylation. We had the one of ozonolysis. That one was done. Then we had the one of what? We had the one of, from before salt, we had the one of acid chloride. So we had the one of nitrites, Grignandi's. So all of these ones, make sure you put them in your head. Otherwise, these methods are very, very important when you come to synthesis numbers. So, yeah. So unless there is a question, but we are going to stop here with the preparation methods. So tomorrow, I think we will look at the chemical properties of carbonyl compounds. So look at the reactions they undergo. So the mechanism they follow, and so on. Okay, unless there is a question, we can easily look at it. No. Okay, seems members have no questions because I'm seeing the chat is is full of emojis. I shared this organic book in that group. Yeah, you can either check the messages and see if you can download it. But I remember to share it there, if at all you were there. Okay, so I think we are going to stop here. If at all there is no question, we are going to end our session right here. Otherwise, we meet tomorrow, but make sure you revise those preparation methods. I told you, don't just look at them and you think you know them. Try to practice them and see if you can write correct reagents, you can write correct formulas of compounds, and you can write correct conditions. But if you just look at them and you read them the way you read other, the way you were reading your history and what, you may not get them unless when you do practice them and you see if you can write correct stuff. Okay, I resend it. So otherwise, I wish you a nice day and a very nice week.
Yeah, it's break time. We can go for break at 10:40. Coming back for biology. So you're free to go and take some tea in case you had not taken. And Mr. Sentai was very ready to take you through biology. Have a nice morning.